Tonight's talk is entitled All About the HR Diagram. I'm pleased to introduce Jeffrey Adkins, who's been here, one of our regular guys that comes here and gives wonderful, wonderful talks. So Jeff Adkins is a teacher at Deer Valley High School in Antioch, California. He teaches physics and astronomy and leads the Academic Challenge and Enrichment Academy. He's also an adjunct professor at Medanos College in Pittsburgh, where he teaches astronomy and physics. He is the author of his own astronomy text called Conceptual Astronomy and a novel, The Boy Who Skipped. He's a former NASA Educator Ambassador and last year's recipient of the Joe Dish Award from MDAS. Now, please welcome Jeff.
Thank you so much again for inviting me. I got a little nervous when I got ready to do this presentation. I get nervous every time because when I talk to students, they don't know anything. I can make up crap and they don't know the difference. But I come here, I can't BS you guys. I have to actually know a little bit about what I'm talking about. But I got nervous because I've been doing so many of these for so many years. I was worried that I've already done this. Like, you know, and then maybe you'd say, well, we just did that a couple of years ago because I've done this particular presentation, at least some form of it in a lot of places. So I went back and actually dug into my records about all the presentations I've done here, and look at that. When it says students, my students did it. So I was able to reassure myself that I have not actually given you this presentation before. So I hope it's new and interesting for you. But back in the good old days, I didn't even speak very much. I'd bring a crew of students and they would come talk about their various research projects. It's been a while since I'd have any students here, but I am delighted to introduce to you a couple of my students here. I've got one in attendance who's not presenting. That's Deja. Hi, Deja. And I've got William and Hannah. Come on up, you two. I told them they didn't have to make a PowerPoint, but they had to talk for a couple of minutes. Tell them what you're up to. Is this on? All right, test. So introduce yourself. Yeah, stand in the light.
Oh, okay. Oh, okay. Hi, Zoom people. Good evening, everybody. My name is William Lee. I'm a student at Deer Valley. I'm one of the students of Mr. Adkins, and I'm doing an exoplanet research project right now. So the thing I'm trying to do right now is obtain light curves of unconfirmed exoplanet candidates.
That wasn't you. Keep going.
Okay. So one of the things you can learn from an exoplanet light curve is the radius of a planet. I use a software called AstroImageJ and Exotic, and you can obtain a light curve from one of the exoplanets. I use there's this telescope network called LCO, which is the Las Cumbres Observatory Network. And once you take an image of that, you can run it through the software and you get a light curve. And then you can learn about, there's a relationship between the flux and the radius of the planets. And yeah, that's basically what I'm doing. And it's just a little science fair project I'm doing.
Hi, I'm Hannah Johnson, and I'm also a student at Deer Valley. My project is a little bit different. I'm a volunteer at Chabot Space and Science Center in Oakland, so I'm sure many of you are familiar with that. And I'm a part of the astronomy team. So every Friday night, we're out there observing, and part of the project we're working on now is basically getting transits of this unconfirmed exoplanet. So we're working with a researcher at the SETI Institute to take images of the transit with unistellar telescopes, which we did about 2 weeks ago. So that was an overnight thing we did, and we took the images, and hopefully we're going to use that to confirm the exoplanet. So that's what I'm working on.
So it's been a while since I've had students who are this aggressively interested in doing work outside the classroom. They are outstanding juniors, so I get another year. But the problem is I'm trying hard to keep up with them. This is a case where, you know, your average everyday student, you got to push them. You have to push them to get them to do stuff. And I do that every day. But these kids, they push me. And it's all I can do to keep up with it. That's the mark of a real scholar, when you're just using every resource at your disposal and pushing to the limits of what we're able to do. So I'm really looking forward to how this turns out and continuing to work with them. Thanks. Deja is also working on a research project. She's trying to measure the rotation rate of the sun, but I won't put her on the spot because I didn't warn her in advance. But she is also doing a research project tracking sunspots and seeing if she can calculate the different rates based on latitude of the sun's rotation. Okay, so let's see. I wanted to show you this. I do have a unistellar telescope that I got with a grant, and I think it might be possible for you to do a Messier marathon and actually take a picture of every one of them, because it's probably the easiest telescope I've ever laid my hands on. Here's a sample of the stuff I got. Most of these are 2 or 3 minute exposures. So there's NGC 2683. That's Ceres. There's Bode's Galaxy. And there's a globular cluster, M92. I'll notice the exposures on these are just like a minute or 2 each. The camera is built in. And while I'm not getting completely perfectly circular star images under high magnification, they're slightly lopsided. I need to work on the calibration just a little bit, the collimation. But I'm pretty happy with it. Some of these are the best pictures I've ever taken of these objects. The telescope has a built-in camera and it auto aligns itself. You don't have to align it at all. It takes a picture of just random stars and figures out what it must be pointing at and then goes from there. I think an experienced person with a go-to telescope that they have polar aligned could be faster. It's a little slow because it checks where it's pointed every time it moves. So it never gets any faster. It always takes the same amount of time to point to a new target. But you can move the telescope and take a picture within about 5 minutes. So it might be possible to get a crude picture of everything in the list. If you were of a mind to do that. I don't know if I'm able to stay up that late, but I haven't done the whole Messier list. I estimate I've done about 50 or 60 of them over the years, but not all at one time. Anyway, I just thought I'd share that with you. Hannah uses these at Chabot. They have a fleet. I have one. They have a fleet of them over there. And she actually taught me a couple of things last time we were working on a telescope together. So I just thought I'd share that with you since that was the topic. Now I'm going to go back to the PowerPoint I'm sharing, and we'll get into the business. So here's our agenda for this evening. How many of you have heard of an HR diagram? And how many of you think you have a passing understanding of what it represents? So some, but not everybody. So there's somebody I can talk to, good. So tonight we're going to, you know, the thing that makes me different, I always wonder a little bit about why you invite me to these things, because if you look at the roster of the other speakers, they're researchers who are using space telescopes and, you know, people who use giant mountaintop telescopes as part of their daily work. And here I am, and I am not a researcher, I am an educator. My research experience is quite limited. But the thing that I do that perhaps the others don't is I make you do something. So you're going to make an HR diagram during the session tonight and see in a primitive way how to make one. And then you'll get the idea from that. And then I can talk about more details. So as usual, if you've not seen one of my presentations before, it's always interactive. There'll be something for you to do in a few minutes, and my students will probably help me coordinate that. Anyway, so we're going to make one, and then we're going to teach you about the quantities that go on the diagram, including the spectral class and what absolute magnitude means. Then we're talking about, once we've seen what the HR diagram looks like, teach you what does it do for us. There are two interesting questions you can, probably more than that, but two of them I'm going to talk about that you can extract from the HR diagram. One of them leads us to the inevitable conclusion that giant stars must exist, a fact that we knew long before we were able to image any of them. You know, you can image Betelgeuse with a giant telescope and get an actual picture of a disk. long before that ever happened, we knew the stars were giants, and the HR diagram is the secret about how we figured it out. The other thing is that it's closely tied in with stellar evolution. So the HR diagram helps us tell the story about how a star dies in particular, and we're going to illustrate that for you. So that's the plan, and I'm going to head and get into it. HR stands for Hertzsprung-Russell, and you don't often talk about the names, we just call it HR diagram, but they were invented independently by two different people. And much like the discovery of Neptune by Adams and Leverrier, they decided to share credit. So it's got HR in the name of it ever since, even though they didn't directly work together to come up with this idea. Hertzsprung developed the diagram in 1911. And among other things that he is noted for, that he did the calibration for Henrietta Leavitt's Cepheid variable method for determining the distances to Cepheid variables, which eventually led to the distances to galaxies. For example, the one that Hubble did, where he measured the distance to Andromeda, and then we established that the galaxies aren't spiral nebulae, but they're actually beyond the edges of our galaxy, and other galaxies exist. You know, that's a surprisingly recent discovery. It was found that we didn't even know what a galaxy was till about the 1930s. Prior to that, they were thought to be nebulas that were just spiral in nature, as if something, a gas was spiraling into the center. So originally they were called spiral nebulae. And once they figured out, using the Cepheid method here that Henrietta Leavitt pioneered and Hertzsprung calibrated, that the galaxies are actually far beyond the edges of the Milky Way, they started calling them island universes. Eventually, they decided to use the term galaxy, which is derived from the Greek and means milk, after the Milky Way. So galaxy means milk as well. Anyway, so Hertzsprung came up with this idea. And then at the same time, approximately a couple of years later, Henry Norris Russell independently invented the idea of the HR diagram. And I find it interesting on his Wikipedia page, one of the things he's most noted for is interfering with Cecilia Payne-Gaposchkin's publication of her discovery of how the composition of the sun is primarily hydrogen and helium. He didn't think that the sun could have more hydrogen and helium than it had heavy metals. And so he intervened as a referee and tried to get her paper squashed because he thought it couldn't possibly be right. And I wonder too if there was some kind of, gender bias thing going on there, if it was just an old versus young thing, I'm not sure. But that's an interesting legacy to have, that you invented the HR diagram and you interfered with one of the most major discoveries we've made in astronomy. But anyway, he gets credit for the HR diagram. He's half of the H and the R, so we'll acknowledge that. Now, the other kinds of information you need to know is where's the data and what is plotted. It's a graph, basically. HR diagram's a graph, and the data that goes on it consists of brightness and spectral class. As you may know, Annie Jump Cannon was the world leader in the spectral classification. She was so good at it, she could glance at a star spectra and classify its spectral class instantly with up to the rate of 200 classifications per hour by 1913. And she was over 95% accurate in her classifications just from memory and looking at a spectrum. Now, in case you don't know what those are, they were originally, the stars have a rainbow, a spectra. There are families of them that are similar. Two stars that have the same spectra have things in common, like their composition and their temperature. So originally, they used the thickness of one of the hydrogen absorption lines to put them in order. And originally they were A, B, C, D, E, F, G. Later on, a discovery that she was a part of became obvious that the spectral classes were closely linked to temperature. So then there came a problem. She'd already done thousands and thousands of spectral classifications on the original scheme of A, B, C, D, E, F, G. And if they're going to change the system to be ordered by temperature, then she would have had to do all of them over again. And they decided it would be simpler just to rearrange the alphabet. So it was actually rearranged in order of temperature, and the letters scrambled and became O, B, A, F, G, K, M. You may have heard the famous mnemonic, oh, be a fine girl, kiss me, or guy, depending on your preferences. That's actually attributed to her. She made that up. So there was a person who created that, and we know who did it. Later on, spectral classes for brown dwarfs were added, and those are classified L and T. So now I tell my students it's, oh, be a fine girl, kiss me like that. But, you know, anyway, here's a picture, a nice picture of a bunch of spectral classes in case you're not familiar with them. And I like this picture a lot because it shows an indication of the different colors. Spectral class is not just a categorical name, but it's also closely linked with temperature and is therefore closely linked with the apparent color of the star. What you see when you look at it in the sky, you see a red star. The first clue you get is that is linked to its temperature. Blue stars are hot, red stars are cool. That is the opposite of Scooby-Doo physics. In Scooby-Doo physics, as you're all probably aware, if you ever fall in a frozen lake, you come out in a blue popsicle, you know, you're inside of a blue popsicle, right? You turn blue. And so in cartoons, blue is cold. They melt you with a red blowtorch, and then somehow you survive that process. In everyday life, we have blue ice in our refrigerator because blue is cold, and our hot water taps have a red dot on them because red is hot. But in stars, it's more like a blowtorch, and the colors are reversed. Blue is the hottest color, and red is the coolest color. So here you can see that the stars at the top, which are category O, have a bright blue aspect, and the red is all but invisible. So those stars to your eyeball, like Sirius, will appear to be blue. As you go down the list, the color that is brightest shifts to the right, and as you reach the bottom of it, the stars at the bottom will be predominantly red, and the blue is almost invisible. So those red stars are basically cold. The temperature range runs from about 2000 degrees Kelvin. Well, you shouldn't say degrees Kelvin. Kelvin is just the unit. 2000 kelvins at the bottom up to over 35,000 kelvins at the top. So this is not only a spectral class scale, it's a color scale, and it's also a temperature scale. You can directly associate each of these letters with a color or a temperature of the star as you look at it. So the sun, as you may know, is a G2. It's not illustrated here, but it's approximately the same as this G5 that you see right about there. And the reason the sun does not have a predominant color, as you can see here, I'm going to say this like 3 times tonight, because I'm a high school teacher, and you have to say everything 3 times. You know, I'll even sometimes literally say to the class, I'm going to tell you 3 times. Here's the first time. And then I'll repeat myself, and I'll say the same thing over and over again and use the same, I'm doing it again. Anyway, so the reason the sun does not have a distinct color is, as you can see here, the bright yellow and green in the middle is pretty bright, but the red is also bright and the blue is also pretty bright. So when you merge it all together with additive color mixing, not like finger paint, all the colors of the rainbow blended together look white. So basically this picture illustrates why you have blue stars, you have red stars that have red but no blue, and then everything else in between kind of mushes together and looks white. So stars are red, white, and blue. I only know of one star that is one of the stars in Albireo, is a double star in the center of the summer triangle. That star, to your eyes in a telescope, that looks yellow. You know, if you look at it, it looks like a golden yellow star, and I think that's pretty rare. I don't actually know why that is, that particular star, but you know, there are exceptions to all kinds of rules. But generally speaking, you know, from just looking at the sky at night, you don't see yellow stars. The sun is not yellow, the sun is white. Sometimes it's red, but that's not the sun's fault, that's our atmosphere, right? So stars are basically red, white, and blue. So we got hot and cold on here, and red and blue and red on there to kind of give you the idea that there's several ways to display this information. So the HR diagram includes spectral class information. You need to collect that data and then somehow plot it. So a couple more slides about this color difference. All stars emit radiation as if they were called black bodies. A black body's definition is not necessarily an object that's black. It's an object that does not reflect light. So if you shine a giant laser at the sun, it will not turn that spot green. It'll just absorb the light and get a little warmer, and then it emits its own color because it's hot. Black bodies do not reflect light. They absorb light and get warmer. So the sun emits light because it's hot. And this particular example, you have blue is dominant and red is recessive. So that's a different way, a graphical method of showing the same thing I showed on the previous slide. I'm telling you twice now. So that's why there's blue stars here, and this one's not red. So if the peak wavelength will shift depending on the temperature, and that will determine the visual color of the star. So you could, and you will, classify the spectral classes of stars by just judging what color does it look like in a photograph. Yes, you are going to do that in a few minutes. Once again, Blue is blue because there's a lot of blue and not much red. Red is red because there's a lot of red and not much blue. But in the red line here that peaks in the middle, everything is kind of bright, so it all blends together and looks white. Now, I told you 3 times, right? Hopefully that'll sink in. Yes.
Does that have any applied to any to a black hole?
No, black holes don't emit any radiation. The question was, do the black body curves apply to black holes? And no, it's just a coincidence that the word black is in it. It's kind of a dumb name because it doesn't look black necessarily. Now, anything dark, like a piece of coal or a piece of shoebox lined with black felt, has a little hole in it, can act like a black body. Because if you had a shoebox with a hole in it, the light can come in the hole, but the felt will absorb the light. It'll never come back out. So the box gets warm, right? Right now, I'm this close to having a really good infrared camera. The school district bought some infrared cameras to scan for body heat during the pandemic, right? And they're wonderful cameras. They're really high-end things. And as soon as they decided that we didn't have to use them anymore, they disappeared. So I'm trying to track down this. So it's supposedly somewhere in a warehouse. And the IT director, the new guy we got for IT, likes me. And I think he's going to give me one of those infrared cameras to play with. And I'm going to mess around with that as soon as I get it. Very instructive to teach the electromagnetic spectrum if you have a good infrared camera. So I'm looking forward to messing with that. But anyway, a black hole is black because it cannot emit light. And if you shine light on it, it doesn't re-emit it like a black body would. A black body would absorb the light and get warmer and emit infrared radiation or whatever color corresponds to its temperature. So a black hole absorbs the light and just keep it, and nothing comes back out. So it's a coincidence that the word black is associated with both, and it's not related. Okay, and please feel free to ask questions at any time, because this is going to go pretty quick. All right, and the other thing that goes on the graph is brightness. Now, it turns out surprisingly that the word brightness is undefined for professional astronomers. They don't use the word. I use it in high school because everybody understands things are bright and things are dim, and brightness means you got more of it. Fine, but it's actually an undefined term in astronomy. They talk about magnitudes, they talk about luminosity. Luminosity is like the wattage of the star. It refers to how many light particles it emits, like a light bulb. And magnitude, I think you're all probably familiar with apparent magnitude, is a rating scale invented by Hipparchus. And wasn't intended as a measurement scale. It was a categorical classification scale. As you may know, the historical invention of magnitude said a first magnitude star is important, and it's like winning first place in a race. So the brightest stars are a number 1. We're number 1 because we're important. The least important stars are given a rating of a 6th magnitude, and those are the ones we typically tell our friends at star parties that those are barely visible to the human eye out at Yosemite. And I keep claiming that nobody, maybe I'm wrong, you can back me up, but nobody in Contra Costa County can really see a 6th magnitude star. The sky in the whole county is pretty much too bright. You got to get away from the cities to see those. So that gives us the classical apparent magnitude of a star. That's a rating system. It's very ancient, and we kept it because astronomers are very traditional. They don't like to change their systems. But the rating system was an importance scale, not a measurement scale. It wasn't intended to measure the stars. It was intended just to classify which ones were important in the constellations. All your alpha stars are magnitude 1 or 2, and on the Bayer system. So the apparent magnitude is the one that most of us are most familiar with because you can point to a star that's the seeing is about a 5th magnitude. You can see a 5th magnitude star, not a 6th. By the way, the Little Dipper is an excellent tool for judging apparent magnitude because it has stars from 2 to 5 in it. So if you can see all the stars of the Little Dipper, you can see down to the 5th magnitude. And the Polaris is the brightest one. It's a 2nd magnitude star. So that can give you a judgment about how bright the sky is by looking at the Little Dipper. Anyway, the original scale went 5 magnitudes is 100 times brighter. We won't get into the arithmetic here, but that does not mean that 1 magnitude is 20 times brighter because it's times brighter and not plus brighter. So it turns out 1 magnitude is 2.512 times brighter than the next. And if you multiply that by itself 5 times, you get 100. This enabled us to, when photography was invented with cameras and digital cameras later, to convert between the visual magnitudes that human beings see with their eyeballs and turn it into a number that a computer can plot on a graph and get a number out of it. Or vice versa. We can take a picture with a digital camera now that provides us raw brightness counts, how many photons hit the detector, and using some mathematical tricks and logarithms, we can convert it into a magnitude that astronomers are used to talking about. We all know what a magnitude is. So we still use that system because, as I said, astronomers are very traditional. They don't like to change their ancient systems, so they can read the ancient records and know what was meant. Somebody 1,000 years ago could talk about a second magnitude star, and we still know what they meant. Anyway, in order for us to use the HR diagram, apparent magnitude is got a problem, and that is because the apparent brightness of the star is greatly affected by how far away it is. If it's closer to you, it looks brighter, and when it's farther away, it looks dimmer. So we have to compensate for that by pretending to shove all the stars to the same distance. And somebody just made up the distance of 10 parsecs. It's just a made up number. They could have picked anything. They picked, let's pretend to shove all the stars towards us and away from us and move them all so they're all 10 parsecs away. And then we can say how bright they truly are, talk more about their luminosity, how much light do they put out, where distance has been eliminated as a factor. So we don't observe absolute magnitudes directly. It's a pretend magnitude. We have to figure it out with math and ask ourselves, how would the star's apparent brightness change if we shoved it either towards us or away from us until they were all 10 parsecs away? And in the mathematical parlance, we usually call absolute magnitude capital M, and apparent magnitude that you see with your eyes and your telescopes is lowercase m. So if a star were 10 parsecs away, then its absolute magnitude and its apparent magnitude would be the same number. There's no adjustment needed. If a star is farther away than 10 parsecs, then you dragged it into 10 parsecs to find its absolute magnitude, you would make it brighter. So that would mean that the absolute magnitude would be brighter than the apparent magnitude in that case. On the other hand, if you have a star that's closer to you than 10 parsecs, you'd have to shove it away to make it 10 parsecs. It would get dimmer. In that case, the apparent magnitude would be brighter than the absolute. Now there's an equation you can use. If you have the two numbers, you could use it to estimate the distance to the star. That's called spectroscopic parallax, but we're not really about that tonight. What we're really interested in is just understanding what absolute magnitude is. And the purpose of having it is so we can do a direct comparison between the stars and know that one is brighter because it really does put out more light, not because it's closer. It eliminates the interfering variable of distance. So if you talk absolute magnitudes, you can pretend that the differences are due to how the star is built rather than to where it is. So for the HR diagram, they decided to use absolute magnitude because then you could have a fair comparison of which stars are truly brighter than the other ones. Now we have all the pieces put together about, what goes on an HR diagram. You can convert absolute magnitude to pure raw luminosity in watts if you like. The radio astronomy people, by the way, they don't like magnitudes at all. It's a foreign language to them. They talk about flux, which is about luminosity and power per square meter and things like that. So they won't even use the word magnitude at all. They look down on the optical astronomers for using that. They're more about watts of power. And it is possible to express luminosity of a star in terms, typically it'd be in comparison to the sun. The sun equals 1, this star is a 5, it's 5 times brighter than the sun. So you can express it in absolute magnitude, you can express it as luminosity in watts like a light bulb, you can express it in comparison to the sun and say it's brighter or dimmer than the sun. However you do it, like I tell my high school students, it's just brightness. You got bright stuff, you got dim stuff. However you decide to display it, that's what it's about. So what goes on an HR diagram? These two things I've been talking about are the data that goes on the axes. Traditionally, you put the spectral class on the x-axis and you start with the hot end towards the origin and let it cool off to the right. So you'll literally go O, B, A, F, G, K, M in that order. As the farther you go to the right, the cooler the star is. You could also put the temperature of the star on that scale. You could also just put the color of the star. And so the left side of this is blue, the right side's cold. And as some of you may know, you can take pictures in the blue and V filters and subtract the two magnitudes you get and get what's called a B minus V index, and that could substitute for the spectral class. There are lots of ways to display this data, but what does it amount to? Hot's on the left, cold's on the right. However you choose to display it, whatever form that data takes, that's an HR diagram. In our case, what you're going to do is use color. We're going to put blue on the left and red on the right, and white goes in the middle. because color is easy to judge. You can do it in a couple of minutes. Our y-axis is brightness, whatever system you choose. Dim is at the bottom, and then bright is at the top. So if it's absolute magnitude, you may be aware that that magnitudes run backwards. So if we used absolute magnitude, we'd actually put big numbers at the bottom because big numbers are dim. 6 is dimmer than a 1. And so unlike a normal math class graph, the numbers are upside down. The dim numbers are big numbers at the bottom, and the bright numbers are at the top, the big numbers at the top. Every year I do the HR diagram activity with my astronomy class. I have to go through and show the kids how to flip the axis upside down, right? They don't know why we're doing it at that level. They're just saying, the teacher said to flip it upside down, so I'm flipping it upside down. They don't really know why we're doing it. They're just doing it because I told them to do it. But I'm kind of a purist here. I want them to look like the graph's supposed to look. So we do absolute magnitudes and we flip it upside down, just like we're supposed to. Anyway, so now we're at the point where we can talk about what you're going to do. So after I explain this activity, we're going to spend a little time on that, and then I'll come back and tell you what you learned. So we're going to analyze the HR diagram by hand for a little cluster known as the Joule box, otherwise known as NGC 4755, or Caldwell 94, if you know the Caldwell catalog. So it's not visible from here, unfortunately. It's a southern constellation near the Southern Cross. But it was discovered in 1751, named by John Herschel. And the activity I'm about to share with you, I shamelessly stole from the National Optical Astronomy Observatory and adapted it for my own book with permission. But it was their idea, and they still have a version of this posted somewhere on their website. Now they're known as Noir Lab, but back in the day they were NOAO, and they did a lot of astronomy activities, and I got this activity from them. Actually, one of my teachers was the author of the activity, Dr. Stephen Pompey, wrote this activity. So anyway, what are we going to do? I'm going to show you this picture. We're going to hand them out here in a couple of minutes. You're going to cut a copy of the photograph like this, and it's got a bunch of stars in a cluster here. The stuff at the edge is probably background stars. So the first piece of instruction is stick to the clumpy stars in the group. Don't do the stuff at the edge. Then I'm going to give you a slip of paper that has a spectral class scale and a magnitude scale on it. Notice that the star number 1 is a big dot, star number 10 is a little dot. It's backwards, just like I advertised. So we're going to play sort of a stellar bingo here. You're going to need a partner to help you out, a paper I'm going to give you, and some kind of a marking pencil. I didn't bring pencils, but I brought everything else. So what you do, you're going to play a little bingo, you and maybe 2 or 3 people, working together. One person's writing all the information down, the others are calling out the bingo letters. So you might look at this little orangey red star. By the way, if it has a fringe around the edge, and for you guys on Zoom, if you go to www.astronomyteacher.com and click on presentations, there are downloadable copies of this document that you can download on your computer. You can do it virtually within PowerPoint. The PowerPoint itself is there. And you can also print the things out if you have a color printer and do it that way. So you don't have to just watch. You could participate if you wanted. So anyway, so what you do is you pick a star and you slide the scale up and down until the color matches. And then you call it out like bingo. K2. Looks like a K2, closest match I can find. And then you slide up the size scale and say, okay, what size is it? And it looks like it might be a 3, it might be a 4. So you make your best judgment. Maybe it's a 4. So you say K2, 4. And your partner who has this piece of paper has the spectral class on the bottom, like a good HR diagram, has the absolute magnitude on the side, like a good HR diagram, goes over to K2, slides up to 4, and puts a dot in the box. It doesn't matter where in the box you put it because you're not plotting it, you're counting it. You're just counting them. She might wind up with 15 dots in one box, and the next box might be empty, but you just put a dot somewhere in the box to count it, right? So you're going to make a series of these dots, and the next question the students always ask is, how many of these do I have to do? When can I stop? And the answer is you can stop when you have enough to make a decision as to how old the Joule box cluster is. And the way you decide that is you look at the answer key. Your graph will turn out like one of these. The one on the left is a relatively young star cluster. The one on the right is a relatively old one, because the HR diagram's first lesson is that it's closely linked to stellar evolution. Here's a rule. If you were taking notes, you would write this down. The bigger they are, the harder they fall, and the faster they do it. That's absolutely true for stars. So the big, hot, bright blue stars, they're like rock stars. They live hard, they die young, and they do it quick. They don't last very long. And the big hot blue stars are up here in the corner. They die first. It's like peeling a banana peel. The top of the peel comes off and the peel goes right down that line. So the farther down the peel is, the older the cluster is. So if you find stars up in the upper left-hand corner, you'll start to be suspicious that perhaps you have a young cluster. If there are none and all the stars are up in the upper right-hand corner, those are stars that are dying or nearly dead. So you're going to plot enough dots to decide. You decide how many to plot. I don't think 3 is enough. But on the other hand, you don't need 100. So you plot enough stars and do a variety. So when you look at this diagram, don't just do the easy ones. Do these little tiny red dots and those little tiny white dots and that little bitty purple one there and that big red one and then one with a purple fringe around it. Do a variety of the stars, right? Spread them around. Don't just do the easy ones and let the rest go. And stick to the middle of the group. When you get to the point where you've made a decision, then the activity is complete. You've decided how old the cluster is, which is the first information that the HR diagram gives us. We love clusters, astronomers do, because they're all the same distance and they're all born together and they're all about the same age. So the differences are intrinsic to them. Well, there really are different stars, right? So it controls interfering variables for our experiments. We can't create stars, but we can choose which one to look at. And we like clusters because clusters are simpler to analyze. You can tell more about a group of stars than a single one all by itself. So that's why we're going to analyze this cluster. So let's get started. I'm going to ask my students, if they don't mind, handing some stuff out. You need a color picture, a graph paper, and a measuring scale. And if you just raise your hand, they will bring the stuff to you. You're on your own for the pencil, though. So let's split up. You got 3 people, 3 things. You do graphs, you do pictures, you do scales.
All right, let's take almost a picture.
And yeah, we'll drop one right there. Can you get that? Thank you, Deja.
All those stars in the same cluster.
Yeah, it's one cluster, except the stuff at the edge is probably in the background, not part of the cluster. We'll get you. Hannah, when you're done up here. You got this? You need a paper, right? All right. William's got it. One up here. We got more pictures if you need them. Anybody else need a picture? A graph paper, a scale?
Oh, they're in here.
I have a Sharpie. That's all I have. Hey, Scott. Thanks for coming. Okay, folks. It's time to vote. See what you think. We can do it with our thumbs, right? So if you think it's a young cluster, you point your thumb to your left. If you think it's a medium age, you point your thumb straight up. If you think it's an old cluster, you point your thumb to the right. So which way do you think? I don't see hardly. I see a couple of thumbs to the right and I see a lot of ups and lefts, right? So it looks like the majority, if I was going to count, think it's medium. A slight majority, a slightly less number think it's young, and a few people think it's old. So, it's not a clear-cut decision, but you might be curious to know what the professionals think when they do an official version of this. They tell us it's a young cluster. And that might be due to the coloration having hard to judge where the blue stars are, but some of those big purplish stars, they're rating them as blue, I think. And so anyway, the professionals think it's young, but you can see, there's kind of a preponderance towards middle and young and not so many towards old. That's how it usually turns out. All right. So if I could get my students to collect the materials, you can keep the paper. We want the pictures back. You can download a copy off my website if you want one to look at. As far as that goes, you could get it from NOAO. They still have it too. It takes a little doing to find it, but it's there. Yes, sir. Oh, it's all done mathematically by pretending. So you do a calculation. You do have to know how far away the star is to do the calculation. It's by basically the inverse square law, by determining if the thing is farther away, it's dimmer. So by using the inverse square law about proportion of the distance is proportional to the brightness proportional to the distance squared, you can calculate what the magnitude is. No, that would be considered interfering. And the interstellar dust reddening and red shifting would cause complications to that. This is for stuff that's more local. You do it for stuff within the galaxy, not stuff that's, you don't do this kind of, if you can't see the individual stars, you can't do this analysis. So it's mainly stuck to stuff in our galaxy and nearby galaxies. It's in our galaxy, right? Okay. Well, we got a little ways to go before we finish the story. So let's tell you a few more details about the HR diagram. Now you've got a hint at how you can use it to judge the age of a star cluster. As you can tell, this method is useless if you only have one star, right? It won't tell you anything about the age. You can only do it for groups. So that's why we like clusters, and the individual stars are more of a mystery to us. But there's other information that you can extract from the HR diagram. Let's stick to stellar evolution though for a minute and look at that. Now, this graph is a graph I also stole from somebody. It's a more complete and detailed HR diagram that includes two different groups of stars. And the circles at the bottom are stars that are nearby us. The stars at the top are stars that are bright to us. So these are not opposite groups. It's not near and far or bright and dim. The top group is bright to us. The bottom group is near to us, and that's done on purpose. I'll explain that in a little while. But overall, let's just look at the general shape. Stars do fall into clumps. There are certain parts of the HR diagram that are uninhabited. There really isn't anything down here. If you learn a little bit more about white dwarfs go down here. But strictly speaking, they're not undergoing nuclear fusion. So in some sense, they aren't stars anymore. But there really aren't any stars. There's a void here, right? They do fall into groups. You may know this diagonal curve here has got a name as the main sequence. And that represents ordinary hydrogen burning stars that are basically adults. They're not brand new baby stars. They're not about to die, but they're just regular stars like the sun. In fact, the sun itself is right in the middle here, right about there. So this diagram, since it reflects our maxim that the bigger they are, the harder they fall and the faster they do it, it is also a map of the stage of evolution of a star, like where is it in its lifetime. The main sequence going from upper left to bottom right represents stars burning hydrogen in the prime of their lives. But they do eventually run out of gas. And when they run out of gas, they change, as you all may well be aware. When the sun runs out of gas, it's going to convert into a red giant. If that changes its size and thus its luminosity, it also changes its temperature. It'll cool down per square inch, but the number of square inches will increase to the point where it actually puts out more light, so it gets brighter overall. That will cause it to leave the main sequence. It'll pop off that line and migrate up to the upper right-hand corner. So the stars in the upper right-hand corner are dying. Their cores have burned out. They're turned into red giants or red supergiants. They have maybe even stopped burning hydrogen in their cores and have gone on to burn the leftover helium from their first stage of stellar evolution. So when they leave, they die, they leave, and they leave from the top down, as we saw in the jewel box activity. These diagrams show you the evolutionary track of a star that's twice the mass of the sun, and another track for a star that's 1.6 times the mass of the sun. The little circle with a dot in it is a universal astronomy symbol for the sun. So when the green line here would represent the main sequence or a little chunk of it, the star turns into a red giant. It'll go up here. It'll run out of fuel, burn up its helium. And if it doesn't die immediately from that, then it will shrink again. And as it shrinks again, it might reignite now the carbon core and light up again. So it'll return to the main sequence area briefly, and it'll zigzag back and forth. The bigger the star, the more trips to the corner it makes. So sun-like stars do it once. They go up and become a red giant. They run out of fuel. The hydrogen turns into helium. The helium burns off. And then the star cools off and becomes a white dwarf. It might hiccup and make a planetary nebula. But that's the end of the story. It doesn't evolve beyond that. Giant star is much bigger than the sun. Some the 7 to 30 times bigger than the sun. They'll go through that gyration several times. When they finally make iron in their cores, you can't make energy by fusing iron. And the star will really die. It'll blow up. You get a supernova, neutron star, black hole. That's a story for another day. But they will leave the picture then. They're no longer a star. They don't make nuclear fusion. So their time on the HR diagram will end. They leave. Black holes don't have spectral classes. Neutron stars don't have absolute magnitudes. They don't glow. So when that happens, they're off the chart. Anyway, so you can track the evolutionary, using computer modeling, our knowledge of nuclear physics. You can calculate the death of a star. I tell my students, we don't live long enough to see the evolutionary track of a star. We don't see them get born, live, and die, because they take millions or billions of years to do that. And our civilization hasn't lasted long enough to watch a single star go through the process. The analogy I use is like if you were an alien coming to the Earth to study the life cycle of humans, but you only get 15 minutes. What would you do? Well, you'd land your spacecraft in the middle of the Super Bowl, and you'd take a picture of 50,000 people all in different stages of life, and then you'd go on about your business onto the next solar system and try to sort the pictures out. You wouldn't have the story of one human being, but you could maybe sort the little people as babies and then grown-ups, and here are the old people, and you try to figure out the sequence. That humans grow up to be about this tall, and then they stop getting taller and they start getting wider. And, you'd learn some things about the life cycle just by looking at the pictures. Yes.
The the spectrum class, do they have any relation to CMBI?
To what?
Cosmic microwave.
Oh, no, there's not a connection. Background radiation is left over from the Big Bang. So the spectral classes are much more local. That's a kind of a universal thing. It's about the whole universe. So the spectral classes are about individual cities. So it's like saying, does it have any relationship to the whole country? And we're talking about individual streetlights in a town. We're just talking about individual light bulbs and not the whole city and not the whole country. So this stuff is kind of local, and CMBR is universal. That's not a bad question though. All right, so I like this little animation. It kind of animates what I've been waving my hands at here for a few minutes. This is not real data. It's computed, calculated spectral classes and temperatures. So we got luminosity now, right? I told you can plot it lots of different ways. And then temperature instead of spectral class. But this is an HR diagram with different stuff on the axes. The same idea. That line is the main sequence. When we animate it, the big bright stars in the upper left-hand corner will die first, and they will move up to the upper right-hand corner, and the line will get shorter as the star cluster evolves. This is calculated, not based on the lifetime of an actual cluster, because we could never see this happen in real data because we only get a snapshot in a moment of time, right? like the aliens looking at the people in the Super Bowl. We don't get to see the star cluster born, live, and die, but we take lots of pictures of stars in different parts of their ages and try to fit them like puzzle pieces into the story. So this is, in comparison, two different star clusters, M67 and NGC188, plotted on top of each other. And you can see now that the two colors don't line up. And that indicates these two clusters have different locations for their elbows. I call it the elbow when it peels off. And the elbow then indicates these are two different ages of clusters. They're different, they're not the same age. So that's a real life data, whereas the other picture was simulated. This is, you know, somebody plotting hundreds of stars using an automated process and calculating the magnitudes and estimating the distances and all of that. So this is real data as opposed to a simulation. That's like an advanced version of the jewel box cluster activity, right? So now the second thing, I think I'm pretty much done talking about stellar evolution in the HR diagram. You can obviously run on and do lots of details, but there's another story I want to tell before I run out of time. And that's the story about how do we know that there are giant stars? And the HR diagram can tell us that. And to understand that, you have to know this rule. Don't wince. I'm not going to make you calculate anything. This is called the Stefan-Boltzmann law, and it tells us how a star's brightness is dependent on its physical structure only on two things. The R is the radius of the star. So in simple English, the bigger they are, the brighter they are. Big stars have more surface area, so they can emit more light. And the T is the temperature. So this tells us that the hotter they are, the brighter they are. Just like a stovetop that you turn up all the way glows brighter than a cold one, or a blowtorch that you turn up all the way makes a brighter light than a dim one. That's cool. So the hotter it is, the brighter it is, the bigger it is, the brighter it is. Now the numbers, the sigma is a constant, 4 pi refers to the surface area. So you don't have to calculate it, just it's R is big, it's bright, and T is big, it's bright. It's all you need to understand about the equation. So we don't really need to calculate any numbers with it, just to understand those concepts. Do notice though, however, if you have something that's twice as big, 2 squared is 4 times brighter. On the other hand, if you have something twice as hot, 2 to the fourth power is 16 times brighter. So temperature is a bigger influence on the brightness of a star than perhaps the size of it. All right, so with that in our pocket, let's look at this graph again. The one I stole from Dr. Mary K. Hemingway, one of the first graduate class I took in astronomy at the University of Texas in Austin. And I did this from her workbook that inspired me to write my workbook many years later. She's aware that I stole her activity. I asked her, can I put this in my book, please? I'll put your name on it. And she says, okay. So this is her activity. I want to remind you that what we plotted here are the stars that are near us, and here are the stars that are bright to us, and they're not opposite groups. But let's look at the stars on the left edge of this. If spectral class is temperature, that means that these little dots at the bottom of the graph are the same temperature as the red dots at the top. They're the same temperature. They're the same temperature. The T's are the same. So what is the only way that the stars at the top, which can be up to 1,000,000 times brighter than the ones at the bottom, how can they be 1,000,000 times brighter if they're the same temperature? They must be bigger. Now, since R is squared, if they're 1,000,000 times brighter, they must be 1,000 times bigger, because 1,000 squared is 1,000,000, right? So there are some stars that are at least 1,000 times bigger than other stars. There are stars that are 1,000 times bigger than the sun. They exist, right? So the smallest stars are 1,000 times smaller than the biggest stars. Ours is kind of in the middle, but the little red dwarf stars, 1,000 times smaller than the red giant stars. And that's just all kind of rounding it off a little bit, you know, we can get more details, but that's the basic idea. This thus indicates to us, the HR diagram is teaching us, before we could ever take a digital picture of Betelgeuse with speckle interferometry and see the disk of it, before we could ever directly measure the diameter of a star, when this graph was done by these Hertzsprung and Russell, we were able to determine that giant stars must exist. They have to, otherwise the Stefan-Boltzmann law is incorrect, and the magnitude system doesn't refer to brightness, and spectral class isn't linked to temperature. They must exist. And there are little stars down here, the white dwarfs are very dim. If you plot them anyway, they show up here. So the blue giants are 1,000 times bigger than the white dwarfs, or more, if you go to the extreme edges of what we've detected. So this is an indication that the giant stars must exist. And I think I said all that. Now, there's a famous YouTube which I'm going to share with you. And you may have seen this because it's, pretty popular. I'm going to let the people in the Zoom see it too. So this little video takes this information and displays the sizes of stars. I'm going to skip all the cutesy stuff. They also include the planets just to set the scale. And just in case you haven't ever seen this, every time the picture animation stops, everything in the picture is at the same scale. So that's how big Pluto is compared to the moon. And that's how big Mercury is compared to the moon. And over here, we have Ganymede, the largest moon in the solar system compared to Mercury. So it's bigger than Mercury. If it orbited the sun, we'd call it a planet. There's Mars, and all the other planets are here. We're going to get the stars pretty quick though. There's Venus, the twin of Earth that's not at all like the Earth. And there's Earth. And then we start getting into larger objects here. This is Kepler 10c, one of the largest known rocky planets that has a surface you could walk on. And then we have Neptune, which is an ice giant, they call it these days. Uranus and Saturn. Yeah, this is a star presentation. Where's the stars? Oh, here they come. A little bit bigger than Saturn, we run into the first of the smallest red dwarfs. They're more dense than Saturn, so that's how come they're still a star. But the smallest stars are around the size of Jupiter and Saturn. Jupiter and Saturn aren't stars because they don't have enough mass. They sometimes say Jupiter is a failed star, but that's not really true. It would have to be 80 times bigger to be hot enough to have nuclear fusion in its core. So it's not really a failed star. And there's our sun. Now we're starting getting bigger stars, a blue giant, blue main sequence star, Sirius, orange giant, Pollux. You can start to see the scale starting to really happen here. This is the size of the giant stars that is implied by the HR diagram. And they get bigger and bigger. So this doesn't last that long. It's not the whole video, but blue hypergiant, they call it, right up in the upper right-hand corner of the HR diagram on the upper left-hand corner. Antares is a red supergiant. And of course, our friend Betelgeuse, who gave us a scare here a couple of years ago, remember? Was it last year, year before? It got all dim all of a sudden, freaking everybody out. And the largest and big star in the Milky Way is UY Scuti, assuming this is up to date. So the rest of this is about scale of universe stuff and not really relevant. But this is just showing you visually what that giant star scale looks like. This is derived from the numbers we got from the HR diagram. So HR diagrams do tell us that giant stars and dwarfs too must exist. Dwarfs must exist. And that's just a graphical illustration of the numbers that we derive from the HR diagram. So things fall into families and they have names. So this is the traditional labeling of the family names within the HR diagram. The main sequence goes down across through here. That's not labeled on it, but we already told you that. The sun's right kind of in the middle. It's the brightest of the nearby stars and the smallest of the bright stars, you might say. It's sort of in the middle of the group. The sun is not an average star, though. I'm going to make that point clear here to you in a minute. Red supergiants and red giants here, hypergiants, if you want to call them that, up in the corner. Blue giants there, red dwarfs there. And if you decided to plot white dwarfs, they'd wind up down here. They're so small, they're very hot, but they're not very bright because they're really tiny. The surfaces are hot, but they're very, very small, so they don't put out a lot of overall light. So this is the traditional labeling of an HR diagram. In a textbook, you'd see something like this. They illustrate it with sizes of dots and colors to show the surface temperature. So this is more of a textbook illustration of an HR diagram. And the names of the families of the stars, they fall into these groups. And there are certain areas like right here that just don't have stars. They don't exist. There are combinations that don't exist. These are the ones that actually exist. It is possible for amateur astronomers to make an HR diagram from your photographs. I provided a link here that you can get from the PowerPoint that I am put on my website. It gives detailed instructions how to take a color photographs and turn them into HR diagrams using specialized software, stuff that you can download. It's possible to do. I just use other people's data because, you know, I'm not that good at photography, but it is something if you were interested in doing, people do it. Amateur astronomers have been known to make HR diagrams from their cluster pictures. Okay, let's see, there's something else I wanted to tell you. We're getting close to the end here. What was it? That's not it. That's not it.
Tell us why the sun's not an average star.
Ah, thank you. That was the thing. So this goes back to this diagram, right? So here's the deal. stars are like celebrities. The bigger they are, the hotter they burn, the quicker they die. So, you know, that's not a bad analogy. It kind of actually happens to stars and to famous people. But you can think of the sun as being like the minor celebrity. And these stars down here in this branch are all physically near to us. So in that sense, they are our entourage. That makes sense? Well, we don't control them, but they're like near us. Everybody knows where the sun is. We're the brightest one in the neighborhood. All the other little nearby stars like Wolf 359 and Luyten 789.6, little red dwarfs, and you know, the sun's the big bright one. They're all little dinky stars near us, you know. So we have an entourage. It stands to reason that if we have an entourage, all of those big bright stars at the top of the graph have an entourage as well. Doesn't that make sense? I mean, if we have one, Sirius has got to have one. And if Sirius has one, Betelgeuse has got to have one. They all have got an entourage, right? But the issue is those stars are not on this graph because I didn't plot them. Dr. Hemingway's plan was to just plot our entourage, because if I had plotted the entourage of Betelgeuse, there'd be another 100 little dots down here for its entourage. And if I plotted Antares' entourage, I'd plot another 100 little stars down there for it. So we didn't plot all of the stars. We selected near stars to us and bright stars, all of which are pretty far away. So if we plotted all the stars we know about, all of them, this bottom right-hand corner gets overpopulated and really thick, but we don't add any bright stars because we already did all of them. Does that make sense? So on this basis, if you did plot all of the stars instead of this representative sample, you would find thousands of stars in this corner, and it would get thicker and thicker and thicker towards the bottom. Whereas the top of the graph would remain the same. We already did all of the bright stars. We did them all, at least the ones in our immediate neighborhood, right? The 500 light years away or so. We did only the bright stars and the near stars that are like 20 light years away or so. And so this leads to the conclusion that if you do statistical analysis, it must be true that little stars are way more common than big stars. Now, if you take an average, that would mean that we are not an average star. We're at the top of the heap of the little stars. There are many more stars smaller than the sun, many, many more, but only a few that are brighter. So to little stars, we're a bright star. To big stars, we're a dim star. We're a median star, not an average, a median. We're in the middle of the range. So I tell my students, it's like going to a kindergarten and an elementary school, primary grades. What's the average height of a person? Well, you've got all these people that are like this tall, right? And then there's one my height in one room. And then the whole school, there's like 15 of us. But the average height is still about the height of a kid because there's so many more kids than adults, right? And then an NBA superstar walks in. He doesn't really affect the average much, but he's taller than everybody. That's the giant star. There's just one of them. Hundreds of us that are shorter. And your teacher, they're not average. They're above average, but they're the middle between the short kid and the NBA star. They're in the middle of the range. So that's an important distinction. The sun is not an average star. It's a median star. We learned that from the HR diagram as well. And it teaches us a couple of implied facts that will help you sleep better at night. Here's one. Giant stars are therefore pretty rare. There's not that many of them. Giant stars are the ones that blow up and wipe out their neighborhoods with supernova explosions and turn into black holes and eat nebulas for breakfast. All those things that are scary about dying giant superstars, we can rest easy and sleep at night because they're all really far away. They're rare. They don't happen that often. So we got plenty enough other things to worry about. A meteor could hit the earth tomorrow, but the giant star blowing up and wiping us all out, yeah, that's not probably going to happen. Nothing that we have to lose sleep over because giant stars are rare, and those violent explosions and black holes and neutron stars that are a result of them are also necessarily rare. Whereas the more common stars that we're surrounded by are just ordinary little red dwarfs and yellow dwarfs. You ever wonder why they call the sun a yellow dwarf? Now you know why. It's not really a dwarf, but it's not really a giant either. It's in the middle. Yeah.
That redshift is above 1 degree or is that very?
That's true in every galaxy, apparently. Now, there are some places where there are a preponderance of older stars, like in a globular cluster. They're all older stars, no younger stars, but generally speaking, yes. Giant stars are rare everywhere. And if you have a starburst galaxy, there's a whole bunch of blue stars that are all of a sudden being born all at once. So two galaxies collide, there'll be a burst of star activity, and you'll get a bunch of extra, proportionally larger number of giant stars, and supernovas will be more frequent. But even in a galaxy collision, you know, the odds of the two stars actually smacking into each other are low. So it's even relatively safe during a galaxy collision. So, you know, they're just completely outnumbered in every galaxy by the little stars.
I had one other question was, when the HR diagram was first invented, did we have an accurate way to measure stellar distances, or did that come later?
Well, you could, parallax predates the HR diagram. So parallax could be used to measure the distances to relatively nearby stars. They were doing parallaxes in the 1800s. So, you know, and later on we used other methods like the Cepheid variable method. If you find a Cepheid in a star cluster, you know the distance to the whole cluster. So you can measure a whole bunch of stars that way, but not every star at first. We had to eventually figure that out. Yes, sir.
It might be pointed out that every star we see with our naked eye, most all the time it's a giant star, correct?
Right.
And so there's very few stars we see that are like the sun or the dwarfs or anything.
Yeah, the absolute magnitude of the sun is a 6. It would be barely visible if it were 10 parsecs away.
Yeah.
So it's, you know, it's not that bright by compared to the stuff you see in the sky. You're seeing the big bright stars in the sky, not the local dim stuff. The nearest stars are all but invisible. Barnard's star, I don't think you can see without a telescope. Any other questions? Because that's the end, but if you have questions, we can take a couple. Yeah.
Is BV Cepheid in the galaxy?
All the ones in the video are.
Oh, okay.
Anything else?
Well, everybody must have got saturated, Jeff.
Yeah, my students say that a lot.
Thank you very much.
I thank my students here for helping out. I appreciate their time. And thanks again for inviting me.
Thank you.
I think it's actually, it's pretty even. I think more girls actually. Hannah? In honors physics, right, that's not. But in astronomy, more girls than boys in the 0 period astronomy. Anybody else?
Actually,
I think we can burn something without having fire, right?
Well, astronomers call nuclear fusion burning. It's just like it's not oxidation. We just use the word loosely. But everybody calls it burning, but strictly speaking, a chemist would object because it isn't really oxidation, it's nuclear fusion. So we'll say the word, but we don't mean what we mean when we're talking about burning a log.
Can't burn without creating fire.
Yeah,
Okay.
if you're willing to change the definition of the word burn.
Well, we wonder what the definition is.
Yeah. Well, to an astronomer, it's not the same definition as to a chemist.
there's a question on the in the chat.
Okay.
Which asks, in the diagram you saw an instability zone.
There was an instability zone. Well, I think instability zone refers to the fact there's a place where stars won't stay very long. They do migrate rapidly when they're in the flux of these changes. So it's an unstable place. It would be stable if it stays there a while. So, they do move relatively rapidly once they leave the main sequence, and then they park for a while until the next fuel supply runs out. So it probably refers to the fact there are places where stars don't linger.
Sure.
But I can't say that with complete authority, but I think that's what that means.
All right.
Now, I remember when you talking about double stars. Is it common or rare? Is it common or rare to have a double star with 2 different temperatures or 2 different spectral classes?
A most excellent question, and the answer is it's perfectly ordinary to have. It'd be weird and rare to have them be the same. That would be unusual just because it's random luck. So most double star systems, the stars don't match. And that would lead to the type 1A supernovas where one star evolves faster than the other. It dies and becomes a white dwarf. The other star evolves later and becomes a red giant after the companion is already dead. As the red giant gets bigger, it dumps fuel on the white dwarf and makes the white dwarf explode. This is what we call a type 1A supernova or a standard nova. They're not quite as incredibly violent ones that the giant stars make. So they're more common, and they always happen in double star systems. And it happens because of your question, because they aren't the same age. One of them dies first. And that's what triggers the whole event.
Would there be anything different about the supernovas because it was two different types of spectrum?
Yes, and a type 1A supernova happens because the white dwarf is already dead and you're dumping fuel on an already dead star. When it accumulates just enough fuel, it automatically blows up because the pressure is just right and there's just enough fuel to do it. So it's always the white dwarf blows up, and it always blows up at exactly the same brightness. So that makes a type 1A supernova as a standard candle. They're always the same brightness. If you see one go off, then everything around it, you can judge the distance to it because you know how far it is because it's always the same brightness when it explodes. The type 2 supernovas, the ones that are the giant stars that blow up violently, they're all different. So you can't judge distance with them as effectively. Astronomers like the type 1A better because they use them to measure distances. One of my own students measured the distance to the Andromeda galaxy by judging the brightness of a type 1A supernova. And you could, it's a math problem a high school student could do to figure out how far away the galaxy is and based on how bright the nova appeared to be in a photo.
Bring that page back up. I wanted them to see what a couple of little people said, that they know why we invite you. Because you're good. Oh, look in the chat.
Yeah, I can see it.
Yeah, he's got the ability to say, okay. I think we're out of time.
Yep.
Okay, Kent has a question, I guess.
Yeah.
Hang on.
Yeah, I think it's a natural
To the
double.
eye, it appears a small blue and a larger yellow.
That's what I see too. And I don't know if it's like, and I've never dug in to find out if it's like spectroscopically yellow or yellow by contrast. And so your eye is fooling you.
Yeah.
But I mean, it is the only star that I would look at and say, yeah, that's a yellow star for sure. Now I've seen it too. They call it the Cal star because it's blue and gold for, All right. Thank you guys so much. Appreciate coming out to hear me talk. Have a great evening.
Thank you, Jeff. And that concludes our program. Good night.
Thank you.
I'm supposed to.